Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. In this lecture video, I'm going to continue with the distributed forces, line loading or surface loading, and the way of transforming that line loading or computing that line loading into a force, single force with specified line of action. And also part of this lecture video would be to discuss about hydrostatic pressure, and which will be discussed in detail in the course hydraulics or fluid mechanics and hydraulics. So this is just uh, a direct way of discussing hydrostatic pressure because the pressure distribution is over a line or a surface or an area or a point, which is important as an application of the preceding topics on distributed forces. Level 61, the conical surface and circular base of the saltwater buoy are fabricated from thin steel plate which weighs 10.2 pounds per square foot. So take note that the weight of this conical surface and circular base of saltwater buoy is a function, the weight is a function of the surface area. So calculate the diameter D of the spherical lead with specific weight 710 pounds per cubic foot, a lead ball suspended from the vertex of the buoy so that the base will be 12 inches above the surface of the water, 12 inches or 1 foot as shown in the figure. So let's draw the free body diagram. Take note that the top surface of this cone is closed. So for the solution, so we have the weight, buoyant force in the conical part, weight of spherical suspended object, which is made of lead, and buoyant force in this part. So the weight of the conical surface is lateral area, specific weight or weight per square foot, 10.2 pounds per square foot times lateral area plus base area. And the lateral area is pi radius times slant height. And the surface area of base area, of course, is area of a circle, pi radius square. So buoyant force in cone plus buoyant force in sphere equals weight plus weight of sphere. Weight of conical surface buoy is 10.2 pi RL, pi times radius 2, square root of 2 square plus 4 square, that's the slant height, plus area of the base, which is pi radius square, and it is 414.79 pounds. Then substitute into this equation. So remember, this is 3 feet, and the volume displaced by similar solids is volume displaced as to 3 cube equals volume of cone as to 4 cube. So volume of displaced, which is V sub C here, as to height cube equals volume of cone pi radius square over 3 times height 4, or as to height 4 cube. So volume of the portion that is submerged in salt water is 2.25 pi feet cube. So the specific weight of salt water, remember, is 64 pounds per cubic foot. So substitute. Buoyant force in cone equals 64 times volume of volumes displaced, which is 2.25 pi cubic feet, So 452.32 pounds. So substitute into this equation. 452.36 plus 64 pi over 6 diameter cube. This is the volume of sphere in terms of diameter, equals weight 414.79 plus weight of spherical object which is made of lead is 710 pounds per cubic foot times volume pi over 6 diameter cube. So simplifying, 37.6 equals 646 pi over 6 diameter cube. From here we can solve for the diameter in feet or fraction of a foot, 0.4808 foot. Then multiply this by 12 to convert it to inches. So in inches, the diameter is 5.77 inches. Level 62. Determine the total force R exerted on the triangular window by the fresh water in the tank. The water level is even with the top of the window, so as shown in this figure. Also determine the distance h from R to the water level, so the distance of the resultant force from the water level. So let's draw the figure in pictorial view here. This is the gate, triangular gate, 3 feet base, 3 feet height. And let's consider that strip. So the pressure over that differential area is constant because the distance from the water surface is the vertical distance is denoted by h. So the pressure is specific weight of water 62.4 pounds per cubic foot times h. So that pressure is 62.4 h and the thickness is dh. So that's dr where the force acts. And this is also h because the ratio of the base and the height is the same. So if this is the height, the base is also h. Then h is equal to h sub c, the distance of the centroid of the differential strip to the vertical to the water surface. So that's also h sub c. Then this pressure is specific weight of water 62.4 times vertical depth h, and R is acting below. The distance of the point where R acts to the water surface is 8 sub Cp. So let's solve for dr first. Dr is pressure times differential area, and the differential area is h dh. Limits for h is 0 to 3. So pressure 62.4 h, then differential area h dh. So using the calculator, we can evaluate this, or we can evaluate this manually also, but to make it fast, because the calculator is allowed, so R is 561.6 pounds. Then by Varignon's theorem, R times h sub Cp equals integral of h sub C differential R, where h sub C is just h. So 561.6 h sub Cp equals integral of h times differential R, which is 62.4 h squared dh. So using the calculator again, 561.6 h sub Cp equals 1263.6. So 1263.6 divided by 561.6. So h sub Cp is 2.25 feet, and this is also the distance big H. Level 63, the cast iron plug, 450 pounds per cubic foot, seals the drain pipe of an open freshwater tank, which is filled to a depth of 20 feet. So determine the tension T required to remove the plug from its tapered hole. Atmospheric pressure exists in the drain pipe and in the seal area as the plug is being removed. Neglect mechanical friction between the plug and its supporting surface. So take note that atmospheric pressure exists in the drain pipe and in the seal. So it will just cancel the effect of this atmospheric pressure. So we just solve for T based on the weight of water, fresh water above the top base, and the weight of the uh, plug, plug itself, which is in the form of a frustum of a cone. So for the solution, we have tension, we have weight of water above the top base of this frustum of a conical plug, and call that weight 1. Then we have the weight of the plug, weight sub 2. So by summing up forces, vertical tension equals weight 1 plus weight sub 2, where weight 1 is specific weight of fresh water, which is 62.4 pounds per cubic foot, times volume, and the volume is volume of this cylinder, pi times radius 4.5 inches, so 4.5 over 12 square, times depth 20. So weight 1 is 62.4 pi 4.5 over 12 quantity square times 20. So weight 1 is equal to 551.35 pounds. Weight 2 is specific weight of this cast iron plug, which is 450 pounds per cubic foot, times the volume of this frustum of a cone. The volume of frustum of a cone is pi height over 3, quantity big radius square plus small radius square, plus the product of big radius and small radius. Then we just express the radii to inches, then divide it by 12 cube for the volume to convert it to cubic feet. So weight sub 2 equals 450 times V2. Again, V2 is pi h over 3, quantity big R square plus small r square plus product of big R and small r, where big R is 4.5 inches and small r is half of 4.5, 2.25 inches, and the height is 6 inches. Then everything is divided by 12. So weight 2 equals 450, quantity pi times 6 over 3 times 12 cube, quantity 4.5 square plus 2.25 square plus 4.5 times 2.25. So that's weight sub 2. Solving for weight 2, it is equal to 57.98 pounds. Then substitute in this equation, we can now solve for the tension. So tension equals 551.35 plus 57.98. So the tension is 609.3 pounds. Level 64, the concept hat is subjected to a horizontal wind, and the pressure P against the circular roof is approximated by P sub O cosine of theta. The pressure is positive on the windward side and is negative on the leeward side. Determine the total horizontal shear Q on the foundation per unit length of roof measured normal to the paper. So here is the given figure and the situation. So for the solution, let's have a differential element, which is a sector as shown, and the length of the arc of the sector is of course radius times this angle differential theta, and the differential force over this differential arc is the length of the arc is r d theta, then multiply it by 1 unit perpendicular to the paper or to the screen to make it differential area. So this pressure times differential area becomes differential force as shown, which is pressure times differential area. So that arc length, differential arc length again is radius times d theta. Then if we multiply that by 1 unit perpendicular to the board as stated here, it becomes differential area, and the pressure is given by P sub O cosine theta, and theta varies from 0 degree to pi radians. So this is the shear, which is equal to Q, and this is the horizontal component of the force after we evaluate F. Then it is F cosine theta, but we have to evaluate the integral of dF. So dF is PdA, dF is PO cosine theta, dA is R d theta times 1 unit perpendicular to the board. So shear is equal to Q equals the component of the total force here, which is F cosine theta. And since differential force is PO cosine theta times R d theta times 1, so the constant here is PO and R. Then we have integral of, so F is integral of cosine POR, then integral of cosine theta d theta. That's times cosine theta for the component, of course. So it is integral of cosine F cosine theta, POR integral from 0 to pi. Then the identity for cosine squared theta is 1 plus cosine 2 theta over 2. So Q equals POR over 2, then integral of d theta is theta, integral of cosine 2 theta is sine 2 theta over 2 from 0 to pi. And remember that sine of 2 pi is 0, sine of 0 is 0, so this term will just give us 0 value. And therefore, for theta from 0 to pi, that's pi. So Q equals pi POR over 2. So that's it for this problem. Level 65, the triangular and rectangular sections are being considered for the design of a small freshwater concrete dam. From the standpoint of resistance to overturning about C, which section will require less concrete, and how much less per foot of dam length? Concrete weighs 150 pounds per cubic foot. So here's the given situation. We have a triangular dam and rectangular dam. The pressure distribution for both is the same because the depth of water is the same. So for part A, let's call this pressure here is 62.4 pounds per cubic foot times depth 24. That's the pressure. And the force F is acting 1/3 of 24 because the pressure distribution is triangular. 1/3 of 24 is 8 feet from the base. Then F, the weight is denoted by WA. It is acting 2/3 of A from C, about which overturning is occurring, possibly occurring. So 2/3 of A, and for part B, this is also 62.4 times depth 24. Then F is the same. This is also 8 feet, 1/3 of 24. And the weight of dam B is denoted by WB. It is acting half of B from C. So B over 2. So this is the reaction at C expected and R sub C expected, which occurs here because it is stated in the problem that resistance to overturning about C is the possible occurrence of what will happen when the depth of water is 24 feet. So F times 8 summation moment about C equals WA times 2/3 of A. That's the equation if we sum up moment about C for this case here. Then F is 1/2 of volume of pressure diagram, so 1/2 of 62.4 times 24 times height 24 times perpendicular to the board 1 foot, so 17,971.2 pounds. And weight of dam A is specific weight of concrete 150 times volume of concrete per foot. So volume of concrete is 1/2 of A times 24 times 1 foot. So weight A is 150, quantity 1/2 of A times 24 times 1 foot, and it is 1,800 A. So apply the equation here. 7971.2 times 8 equals 1,808 times 2/3 of A. So from here we can solve for A. A is 10.946 feet, and therefore weight of concrete A per foot is 1,800 times 10.946, and it is 19703 pounds per foot. For part B, weight B, F times 8 equals weight B times B over 2, where weight B is 150 times B times 24 times 1. So 150 times B times 24 times 1. So weight of dam B is 3,600 B. Substitute here, where F is the same, 7971.2 times 8 equals 3,600 B times B over 2. So B is equal to 8.937 feet. Then weight of dam B per foot is 3,600 times 8.937 feet. So weight of dam B per foot is 32173 pounds per foot. So it is A that is the dam that requires less concrete than B, and the difference is 32173 pounds per foot minus 19703 pounds per foot. So the difference is 12,470 pounds per foot. So therefore, our answer, dam A, requires 12,470 pounds per foot less concrete than dam B. So dam A requires 12,470 pounds per foot less concrete than dam B. So that's it for this series of sample problems.